let's finish with energy balances. And where were we? We were, oh, before I change the screen share, let's see. Question for you guys. Let's see how we're doing. There is one equation of life in this class. This one equation that is the most important equation of all. And the equation that if we don't ever know what to do, that's what we do. And anybody can give me a quick, maybe on the chat, an indication of having a sense of what this equation would be. Thank you, Ibrahim, for the suggestion. Is even more fundamental than that. All right, I'd love to hear from one more. So this class is not so rigid. Yes, thank you, Nolan. Brownie points for you. No, Bernoulli's. We never talked about Bernoulli. Bernoulli is for fluid mechanics, and it's for very particular conditions. The equation of life in this class, to which we're, every time we don't know something, we'll come back, is this. This is a Bible for us, the Quran, the Torah, whatever it is. This is what it is for us. And if you don't care about heat transfer, this is the equation of your bank account. And let me tell you, if you don't know heat transfer, it's sad. But if you don't know your bank account, that's a real problem. So now, this equation, I just wrote this equation, but this equation makes no sense unless there is something else with it. What is it? All right. Well, this equation makes no sense unless there is something else with it. Control volume. Thank you. So what I see from some things I'm reading here in the chat is that you guys came like with some background of fundamentals of fluid mechanics or like a Calc 2, something like that. And of course, boundary conditions or Bernoulli equations matter. But here in heat transfer, and actually much of life, is an equation of conservation what matters the most. You cannot generate energy when you didn't have it, right? You cannot gain or lose mass. And in this class, of course, we're not going to be dealing with like nuclear reactions in which mass and energy are equivalent. We're not going to worry about those. We could if we wanted, but we don't want. So this equation says nothing and says everything. This equation just says energy is conserved. That's like saying nothing. Although if a couple hundred years ago, people were not sure about this. So this is how powerful this is, right? Like humanity lived for thousands of years clueless, but the last 200 years, we know energy is conserved. And now I'm trying to teach you these 200 years of heat transfer in one term. So it's tough. And control volume, let's make our potato that is essentially a non-committal shape. And here we have our control volume. And in this control volume, we have Q coming in or Q coming out, right? Heat generated would be inside. and the energy stored is the result, what the material experiences as heat accumulated in the form of enthalpy. So we the reason this equation is so powerful, because now we can go and later on in the class we're going to say, okay, what are my mechanisms of heat coming in? What are the mechanisms through which heat goes out? What are the mechanisms of heat is generated? That goes into the physics, the generation. So that in this class, I would give that to you. But in real life, you would calculate this resistance heating, nuclear decay is the heat from a chemical reaction, right? And good. And for the sake of review, so we said, okay, let's forget about Q in and Q out and Q generated for now. Let's look at just the Q stored. And for the Q stored, we have this relationship between temperature and enthalpy. And if you remember, I is not the imaginary number, I is enthalpy, and we don't use H, that is the most common notation, because we're going to save H for the convection coefficient. So the units of enthalpy are joules of thermal energy per kilogram, and the units of temperature, let's say degrees C, could be Kelvin, could be many. And then we saw that with more temperature, we have more enthalpy. And this slope, okay, who tells me what this slope is? The slope of enthalpy versus temperature. Yes, thank you so much. Thank you so much. I haven't said if this is solid or liquid or gas, so let's call it C, specific heat. And if we have a phase change, in this case for a pure material is vertical. If it is an alloy or a mixture, actually is not quite vertical, not exactly vertical, right? And so if we say this is specific heat of the solid, say this is specific heat of the liquid, my question to you is, what is this called? Latent heat, what would be the symbol? Thank you so much. You guys are super awesome. We're doing super well. This is still like the easy part of the class, but I cannot afford to lose anybody right now. Good. So we're doing super great. And we did an example in which we calculated melting ice from -20 to +20. And just using these concepts and the values of specific heat that are tabulated in the book or on Google, like by now, those things are mostly universal. You can make calculations in which you keep numbers. If you know how many kilograms of ice you have in your boots when you came home, after it melts, you know exactly how much energy you wasted from heating your house into just melting ice that you didn't need to melt. All right, good. I'm leading into the last part of where we stopped last class, and we had our equation of life, Q in minus Q out plus Q generated equals Q stored. And we said this depends on a control volume and also between time 1 and time 2. This is like relativity, time and space. Time and space are very delimited between time 1 and time 2 and inside the control volume. We said, what if the time interval, time 1 and time 2, are very close to each other? Of course, that's the old trick of doing a differential, right? So I would divide all this by delta T. And the small amount of heat that came in this amount of delta T would be V of Q in over dt, right? You have seen this many times, and the same with these other parts here. This, we're gonna give a name, and we're gonna call it the small q, q in. And this has units of watts. Big Q has units of joules. All right, so now I'm gonna switch to our notes and go over that. Change here. All right, so equation 42 is what I just did, and equation 42 is what we just discussed, and that ends up turning our equation of life into a different expression of the same equation of life. Now, instead of being an account in total joules, right? Like in your bank account would be in total dollars. The energy rate would be how many dollars per month you get, right? This would be more of a budgeting exercise, right? So how many watts you come in, how many watts go out, how many watts are generated, how many watts are being stored. All right, so then, much like we did before, I want to focus on the heat stored. And the heat stored now would be a rate of heat stored. And in the heat stored, we said what matters is mass and enthalpy, both things, mass and enthalpy. And when we do a derivative of two things that are multiplying, now it gets interesting because one might be constant and the other not. Maybe neither is constant. But let's take one at a time as constant. And let's start with a case in which we have an open system in which mass is coming in, right? And if mass coming in or coming out. So what do we call, I would love to hear a word from you, what do we call the transfer of heat by the motion of mass? Advection, thank you, super awesome. That's the name of the game. Like and most books, the heat transfer book that I recommend so highly uses the word advection once in the whole book. In reality, it should have been a chapter, but they use the word once and just randomly. So this way of transferring heat is essential for us. And so if the amount of mass is coming has the same temperature of the amount of mass that is inside, then this rate of heat is the mass flow rate times enthalpy. Word mass flow rate, you're going to hear that so much, especially those of you in chemistry, because that's how heat exchangers work, right? You put mass in and it exchanges heat. So this mass flow rate, m dot, times the enthalpy with which this mass is coming in. All right, if I have mass coming in or out of our control volume, it's an open system. So now let's talk about a closed system. In a closed system, mass does not come in or out, right? The mass that is in there is in there. The control volume, something I put in the notes, but I didn't mention explicitly. The control volume can become bigger, can become smaller, right? For example, if I have some gas expanding, the control volume can track that expansion and the mass would be the same, right? And it's still a closed system, right? So let's talk about a closed system, and so the Q store. Oops. Oh, Nice. Okay. The in a closed system, the mass now is constant, but it's the enthalpy that is changing, right? And look at this. This is the chain rule you knew from calculus, and you probably were also glad to have forgotten. But actually, there was a point to it, and it's useful because look at this. You know, just from the definition, the very basic definition we have, that the heat stored, if there is a closed system, is mass times change of enthalpy. I'm saying nothing about phase change at this stage. This is universal for any type of system. Any type of system. Now look at this. Let's use this our good friend, the chain rule, and we have mass times, and instead of di dt, I'm going to do variation of enthalpy with temperature times variation of temperature with time. So those of you who remember calculus will know this is right, this is true. But this little trick is so insightful. Look at this. di dt, as you just told me before we started the formal lecture, you know that the derivative of enthalpy with temperature is specific heat, which is tabulated. So that derivative, we know because we go to our heat transfer book or to the internet or to the amazing databases we have in our lab, and you can get this specific heat, no problem. And then we have variation of temperature with time that I put here as T dot, that's the same thing. That's what you measure with a thermocouple, or what you measure with a pyrometer, or what you measure with a thermometer. I can measure that very easily. So all of a sudden, I turned a concept that is kind of abstract about heat stored in a closed system with no phase change. I'm turning into something that I can go to, I can, and mass, I can either measure the mass or say it's volume times density, right? I can have like a measuring tape and measure volume. I can get the density and specific heat tabulated from Google. And so far I spent between $0 and $1 in the ruler. And then I can spend $50 in Home Depot and get a multimeter with a thermocouple. And all of a sudden, I'm measuring heat stored in pretty much any system as long as there is no phase transformation. So powerful, and don't be fooled by the simplicity of these equations. All right, so let's, I'm going to go through an example. If you remember, an example we didn't have time to do on Wednesday was how much heat we needed to get water from 20 degrees to 100 degrees. I hope you took a look at the notes, but if you didn't, that's okay. It's all in the notes. I was hoping to do it in a more interactive way, but as I'm learning, teaching online is sometimes it's slower, and my handwriting is not as beautiful. All right, so what is the power needed to heat water to make pasta, right? And we know this. We know we have this is 1 gallon of water, that is 4 liters of water, that is 4 times 10 to the minus 3 meters cubed, right? From 20 to 100 degrees. And we know from the previous calculation of Wednesday that would take 1,300 and something kilojoules, right? This is amazing. We can say how much energy it went into heating up this water. If we say it takes 10 minutes to heat this up, and by the way, these 10 minutes are more or less right because I timed it in my kitchen, right? What is the power in kilowatts? So I need to know how many kilowatts I need in my range to bring up the water from 20 degrees to 100 degrees, a gallon of water from 20 degrees to 100 degrees. So control volume is what we start all the time. And let's make a control volume, because we can say nothing without a control volume, even if it is a potato. No control volume, and you don't know what you're talking about. So the control volume, this is my attempt of a pan. This is the water here. And let's call it water. This is my pot. And I'm going to make my control volume here. My control volume, going to make it slightly inside the water. Remember, I told you it's never on the line. It's always a little bit inside or a little bit outside. And the reason I do this is because what is inside the control volume? Only water. If the control volume was a little bit outside the water, getting a little bit of the pot, then now I need to account for the mass of the pot and the thermal properties of the pot, but I don't want to. So I chose this control volume. So this was my step number 1. Step number 2, equation of life. And because they are asking us about a power is a rate. So we're going to use our equation for life for energy rate. So Q in minus Q out plus Q generated equals Q stored. By the way, during the Christmas break, I did some consulting and I was paid quite okay for a big company. And you know what we were doing? We used this equation to make calculations that are useful for welding in real life. This equation is powerful. This exact equation with the same notation. All right. So the problem asks for the calculation of Q in. How much heat do I need to put in, right? That coming out from our range. So I wrote the equation. We said that assuming our water is not radioactive, we don't have a heat generated here. So I'm going to say that's 0. I'm also going to say, just now, and because we're taking baby steps in this class, I'm going to say that there's no heat losses. Is it true? No, I'm lying. But it's a good lie, because reality is not all that different from this. Why is it a lie? Because in reality, we do have heat losses. If the pot is hot, it's losing heat towards the colder air outside, right? By convection, which we'll study in detail later. It's also losing heat by radiation, because the surroundings are more or less 20 degrees and the pot is starting to get to 100 degrees. And in addition, even before we reach 100 degrees, we already start to evaporate water. You know this because, and if you don't know, do this experiment tonight. Put some amount of water on a plate, right? And not a lot of water, some water on a plate. Leave it on beside your bed before you go to sleep. And when you wake up in the morning, check it out. The water is going to be gone. So the water evaporated, but it was never boiling, right? So the water evaporates, and when it evaporates, takes heat with it. And in this particular case, we're going to say that amount of evaporation is too small. Later on in this class, we'll be able to calculate all of that. But right now, I'm going to say it's gone. So we end up with this equation. Let's see. Here we go. Erase. So much for making all these drawings, and now I have to erase them. All right. So what are we left with? We're left with Q in equals Q stored. By the way, in problems this simple, I don't even need to do all this formalism, right? I know it in my head. And chances are that intuitively you would have done the same. And intuition is amazing, never lose it. My hope is that in this class, we're going to take your intuition to the next level. Without losing your intuition, you'll be able to expand it to things that most people would not be able to imagine. So Q in equals Q stored. And we know Q stored was this derivative of mass times enthalpy with time. And because we just did it, we know that we can express this as volume, a gallon, times density of the water, a kilogram per liter, or 1,000 kilograms per cubic meter, the specific heat that is tabulated, and the temperature rate, the rate of increasing temperature, which I can put it thermocouple, thermometer, anything, maybe even one. Oh, do we have to show all the steps on assignments or on exam? The answer is yes. In the exams you're going to have in this class, because it's all online, you'll just have to give an answer. And I'll give a range of plus minus 10% for the number you calculate to be right. In the assignments, that's not so rigid. And in both assignments, you will have to show all steps. In assignment 1, you can do them by hand in a way that is legible, and you have to scan it in a way that is legible and send it to us. That's a traditional assignment. Assignment number 2, you're going to write it like a professional report, in which you're going to show each step, much like I'm doing here, to show your credibility the way you would in a consulting report or in a report to the management in the company you work with. Did that answer the question? Awesome. So what is the rate of temperature increase? If we say that once we turn our stove heater stays at the same place, then we can say that the amount of heat into the pot is constant. Whatever it is, we're calculating it, but it's constant. It's not changing. And so if Q in is constant, because we're not changing our knob, then volume is constant, density is constant, specific heat is constant, then the rate of temperature increase is constant. So many degrees per second all the time. And of course, you're going to see that there are subtleties about this, but I'm not worrying about these subtleties right now. If it is constant, the differential, the derivative is the same as deltas. And I know the delta T is going from 20 degrees to 100 degrees. And the time is 10 minutes. So I plug and chug, and I get this number. Q in is 2.23 kilowatts. And you know a cool thing about that? So then I went and checked in the power of an oven range. And sure enough, that's the way I did it is by checking the circuit breaker. Yeah, and it's pretty much what you see in reality. So what have we seen here? That the equation of life coupled with some tabulated values of specific heat or densities that you can find anywhere in your book or in Google lets you predict the circuit breaker you would need in a kitchen oven. I think that's awesome. That is only our third class, and you already can say something that, for example, an electrician would know, but would never know why. All right. So my suggestion is that in practice for the exams, you go over these same things and you try to do them yourself, and you do step by step until it's ingrained in you. There is some amount of training, as if you're playing an instrument. You do it enough times until you don't think about it anymore. Cool. The other thing I wanted to mention is degrees Celsius and Kelvin are tricky to convert. If I tell you is 20 degrees Celsius, I'm comfortable. Chances are that's what is in this room right now. If I tell you it's 20 degrees Kelvin, chances are I'll be chilly, right? It's gonna be cold. You know that because there is a difference of 273. But if I tell you that this room got cold, if I open the window and the temperature here goes down to 19 degrees, I have 1 degree of temperature decrease, right? But 1 degree of temperature decrease, you cannot do the minus 273. It's not minus 272 degrees of temperature decrease, right? The delta T, the changes in temperature, delta T's, or differentials of temperature, are exactly the same in Celsius as in Kelvin, right? So when I have a temperature rate, or when I have something that is joules per Kelvin, things like those, is the same as joules per degree C, because all refer to delta temperatures. The only time in which you need to worry about the 273 is when you're talking about an absolute temperature. Is it 20 degrees or is it not 20 degrees, right? If it is 20 degrees C, to convert to Kelvin, you need to do the 273. If I say the delta T were to be 1 degree, or the delta T were to be 20 degrees, you do not use the 273. Again, sounds trivial. Enormous amounts of points are lost in exams because people put the 273 on a delta when it shouldn't be. Okay. So far so good. Any feedback? It's so terrible to just listen myself in a room here. All right, good. So now let's say something that I experienced firsthand, and maybe some of you did. Have you ever put your water to make pasta? You turn on the heat and then you go do something else, only to forget to come back and you realize the water is gone and you ruined your pot, right? So, how do we calculate how long can we go and forget things before we evaporate all the water? We can do that right now, and that's something I want to do with you. So we reach, in the same example we always have, we have reached 100 degrees, but we just happen to be on Facebook or whatever, and we forgot that the water started to boil, and little by little, now we're accounting for evaporation. 100 degrees, boiling point, let's say now it evaporates for real. How long would it take? How much how long can I be distracted before I have to pay a price? Let's do it. In this case, whoops. Look at this control volume. The control volume is pretty much the same as before, except there is a subtlety here. Look at this subtlety. You see that you see that the control volume goes inside the pot. So I don't have any pot material inside my control volume. But look at the top. So what's coming out from the top? What's coming out from the top is vapor. It's not liquid water. And that matters. Had I made the control volume just inside the water, then we would be a very different problem. In the end, the answer is the same, and you can solve the problem both ways. But I'm doing this with the control volume just outside. Okay, so given that we have a control volume, and that's our stage 1, right? Step 1, which you will do in your assignments, and hopefully you'll do in a scrap of paper during the quizzes. I have no way of checking, but I really hope you do. So step number 2, yeah, energy balance, because they asked us for power to evaporate. So we use the equation of life in rates. Q in minus Q out plus Q generated, Q stored. I don't know how many more times I'm going to be saying this, right? It's, okay, let's get this out of here. Because it's a mantra. It goes, now we know this. We know from the problem we just did what the Q in is. We know we're putting 2.230 kilowatts. We know, we just calculated because it was the power we needed to get to 100 degrees. That power is still on. The difference is now we don't keep increasing the temperature anymore. The water is not going to be at 110 degrees. So I need to raise this here now. And okay. So we have Q in that we knew. It's 2.2 something kilowatts. We knew. Do we know Q out? Yes, we know Q out. And we know Q out is the where we have it. Q out is, and because we saw it in the equations for an open system, because we have mass leaving our control system, is the flow of mass times the enthalpy of the gas. The gas is leaving with enthalpy of the gas. That's what's crossing the control volume. And I put a minus sign here. I put the minus sign because Q in is a positive magnitude minus Q out. So Q out is a positive magnitude. Now, m dot, because the mass is decreasing, m dot is a negative number. So this is minus a negative number because m dot is negative. Minus the negative, that would give us the positive value that Q out should be. And then we say Q generated equals 0 because we agree that our water is not radioactive. And so we end up that the Q in equals the Q stored, and the Q stored in this case is this d of mi dt. Quick question to you. Does the enthalpy change in this problem we're considering of boiling a pot of water? Yes or no? Oh, here you have it. So we can make a yes or no here in the on the reaction side. So does enthalpy change or doesn't it in this problem? You can use the reactions and tell me yes or no. Wow, you can use the chat. I don't see the reactions. All right. Really, nobody wants to take a venture here of if the enthalpy changes or not? So let me give you a clue. Does the temperature change or not? Is the temperature of the water changing? No, of course, the water is not changing temperature. It's at 100 degrees. And liquid water at 100 degrees has a fixed enthalpy. So the enthalpy is not changing. So all is changing is the mass that is leaving. So in this case, we have the Q stored is in this case is this mass times the enthalpy of the water. right? This horrible notation, F stands for the liquid. So I would say Q in, which we know from the previous problem, plus, minus Q out, and it's minus Q out, but if you remember, there was a minus sign there, so it's plus this m dot here, times the enthalpy of the gas equals the mass flow times the enthalpy of the water. So I can operate here, passing things right to left, and you can do that. I really suggest you do it in a piece of paper at home. And what do we end up? We end up that Q in equals the mass we had originally, the time it takes to evaporate, that is this delta T, times the latent heat of vaporization. Please take a very quick look at this, because it seems easy, but it's deep. And from here, we can calculate the delta T. Solve for delta T, and I plug and chug, we put the numbers in there, and it gives me 67 minutes. So at the minute 68 of Facebook, you ruined your pot. And by the way, yeah, I know for a fact that this is more or less right. That's amazing. Day 3 of heat transfer class. You can calculate the circuit breaker you would need in your stove and why. And you would know how long you can leave a pot unattended before you run into trouble because of evaporation. None of these things are trivial. So here for the MADIs especially, the heat transfer during a change of phase is very important, because it's what happens when you go from austenite to ferrite in a quench operation. Is the heat associated with solidification and melting. I'm not going to go into detail of this in the lecture, but it's here for all of you, right? And in the chemists too. Just here is how you understand how much liquid and solid you have, right? Or so much of two phases, how the phases are changing as you add or take away heat. It's all in the notes, all in good, that is in detail in the notes. So in these last 3 minutes we have, I'm going to tell you the last thing is rate of heat transferred by advection. So let's say we have a pipe that can be the pipe of a heat exchanger. So by the way, the dean once told me that as long as you guys knew how to understand heat exchangers, that's success in this class. And you know what? Today you do. And then we'll have a whole unit on heat exchangers. And the whole class will be oriented towards understanding all the details of heat exchangers. So let's say this is a pipe of a heat exchanger. And let's see how heat is transferred. And so far, I'm not talking about what mechanism is the transfer of heat. We'll see that next week. But we know whether we gain or we lose heat. I don't know how, but we know we do. So in this heat exchanger, you have some amount of mass. I take a control volume just inside the pipe. And we have some amount of mass coming in. And if there is no leaks, it's the same amount of mass coming out. But there's a trick. Let's say we have T1 is a hot temperature and T2 is a colder temperature. So water comes in at a temperature and comes out at a lower temperature. That means it lost heat. And that loss of heat is this Q loss we have here. I'm not saying what mechanism it is, but I know it's losing heat. That's a fact because the temperature is lower. So given that I have done my control volume as a step 1, and I write my equation of life as step 2, and then I look, okay, is there Q generated? No, no radioactivity or anything similar. So no Q gen here. An interesting thing, is there Q stored, a rate of heat stored in here? And because I'm running out of time, I'm going to tell you the answer straight. No, there is no rate of heat stored. And you know why? It's true that heat comes in and it's true that heat comes out. But But in a heat exchanger that typically works in steady state, once you establish the thermal regime, it stays the same in time. It gets at a temperature, gets at another temperature, but nothing changes. So because temperature is not increasing in time and temperature is not decreasing in time, we have no rate of heat stored. We're not gaining heat. We're not accumulating heat, right? So heat stored is 0. This I said very quickly. Is not trivial. Please take a very quick look at the notes. I wrote them with lots of love. So if you read them, you'll make me happy. And you're gonna see then if this Q stored is 0, we end up that this balance that says Q in equals Q out. And we're gonna stop here, but very quickly on Monday, we're gonna wrap up on this before we get into the new topic of heat transfer mechanisms. Thank you, everyone, and I wish you a great weekend.
Thank you.
Awesome, thank you.